Hello everyone, I'm Yumingzhi from Southeast University. Today I'm going to present our research on real-world IoT attack concealed within the Tor network. This is a joint work with Drexel University and UMass Lowell. To understand the problem, let's first look at two different IoT architecture. First is cloud-centric IoT devices, commonly with limited capability and located behind the net, rely on cloud server for communication and data processing. In contrast, cloudless IoT devices like NAS or DVR can be directly exposed on the internet. This gives the user more control and can reduce privacy concerns associated with cloud providers. However, this direct exposure to the internet also makes them valuable targets for cyberattacks, and this is a specific threat we will be exploring today. Another key component in our research is Tor. Tor is a powerful and widely adopted anonymous communication system designed to protect users' privacy and freedom online. Based on onion encryption and routing process, Tor traffic can be divided into two types. Internal traffic, transmitting between onion router and onion router, is encrypted, and external traffic, which flows between exit router and destination server, is no longer protected by Tor's encryption. Our laboratory ran several Tor exits, and when we detect IoT traffic on these routers, it raised a critical question. Why would anyone need the anonymity of Tor to access their own IoT devices? Our investigation into the traffic revealed a concerning reality. To avoid detection, hackers are leveraging Tor's anonymity to exploit zero-day vulnerability against cloudless IoT devices. And here are two real-world examples from exit routers. On the left is a request exploiting a zero-day information disclosure vulnerability, exposing not only the credential in plain text, but also the device model. On the right, attackers were trying to exploit a zero-day commit injection vulnerability to implant a PHP backdoor. Consequently, we think that if we can analyze the traffic passing through Tor, we might uncover the vulnerabilities being actively exploited by these malicious actors. The RB deemed this research not human subject research, but we were dealing with real-world data, so we took extensive precautions. We kept data confidential and secure, and Tor's inherent anonymity ensures the privacy of users, and no personal identifiable information was ever analyzed. But still, we faced a variation of trolley problem. On the upside, it offers significant security benefits. It enables responsible disclosure for public safety and adoption for intrusion detection for Tor. However, on the downside, we need to analyze the data from a system designed to ensure privacy and anonymity, and we recommend that future researchers consulting Tor Research Safety Board when planning related studies. To tackle this challenge, we introduced TORCHLIGHT, a system designed to collect, discover, and analyze IoT attacks at TORCHLIGHT. TORCHLIGHT consists of three components: TORCHLIGHT traffic collector, deployment planner, and ARM-based IoT traffic analyzer. Our TORCHLIGHT traffic collector runs on resource-limited VPS, so efficiency is very important. As mentioned earlier, we only need to capture the encrypted external traffic, and this can save us about 50% of our storage space. As you can see in the table, we can distinguish internal and external traffic based on whether the source and destination IPs are both Tor relays. But there are more than 7,000 discrete Tor IP addresses, so we use IPsec, IP-table extension, to perform this check in the OS kernel, leveraging its hash structure for fast access. First, we fetch Tor consensus file, and then we add rules to IP tables with NFQ target, and then we snip, store, and send this data to our local NAS using an encrypted SSH channel. However, only capturing external traffic is not enough. There are still lots of noise and information we don't want to interrupt. So in this step, we further filtered out irrelevant data. First, we filter traffic using common IoT protocol like HTTP, RTSP, FTP, and Telnet. Then, we empirically filtered out irrelevant data from three perspectives: top 1 million websites, hosting providers, and error responses. Next is the deployment planner. Based on the source code, we study the exit router selection algorithm, indicating that the router with higher bandwidth get higher selection probability. However, our relays are low bandwidth VPS. This means our relay naturally have a lower chance of observing attacks. So the goal of our deployment planner is to solve this problem by maximizing bandwidth on fixed budget by deploying the most cost-effective nodes. And for the detailed algorithm, please refer to our paper. Next is the ARM-based traffic analyzer. Detecting attacks at Hongze is an open-world problem because we don't know how attacker will attack and which device will be targeted. Therefore, we adopt a 5-step chain-of-thought process to first identify IoT traffic and then detect attacks. First, we preliminarily identify IoT vendor, type, and model information in the responses with in-context learning. And then we prompt the LLM to re-verify the IoT entity it has recognized previously, addressing the hallucination problem. However, sometimes we may only identify a device model. For example, here we may only identify the IPC HFW in the response, but its vendor and type are still missing. So in this step, we use RAG. We harvest latent document like title and snippet from the search engine, and we give this information to the LLM and prompt the LLM to complete the missing vendor and type information. Even though similar identifying IoT entities in responses doesn't confirm the traffic is IoT generated. The above example shows traffic from a blog post that mentions a Sony camera. Our earlier step would identify the device vendor and model. But we can see this is a blog post. It's not an IoT generated content. So in this step, we prompt the LLM to make a judgment. Does this response originate from an IoT device itself, or is it just a web page discussing the device? Finally, once we have confirmed the traffic is an IoT device, we analyze it for attacks. We prompt the LLM to perform binary classification based on input to identify attack types, and the input vary for different types of attack detection. And here is an example of commit injection. We prompt the LLM to determine if there is evidence of commit injection. From the answer, we can see that the LLM can not only identify the attack, but correctly identify base64 encoded command and further infer its meaning. The same method is applied to other attack types like information disclosure and path traversal. Now is evaluation. First, how effective is TORCHLIGHT? Over 12 months, we developed 3 exit routers in Las Vegas, New York, and Miami for just under $200 and collect over 26 terabytes of traffic. For ARM-based IoT traffic analyzer, our IoT device traffic detection achieved over 93% accuracy, and attack detection results are also very good, with commit injection detection, for example, reaching 99% accuracy. Next is which type of IoT devices are most frequently accessed within the Tor network. We discover traffic from over 50,000 unique IoT devices across 148 countries. Digging deeper, we found that the vendor and type distribution follows a long tail, with only a few manufacturers like CoreVision and a few types like DVR and camera were being targeted. What's more, we found most of the traffic is brute force login attempts, and for ethical reasons, we focus on analyzing credentials using the field login attempts. We found that top 10 of the non-directory passwords are related to specific device brands, like Link and TP-Link. This shows that attackers are not just guessing blindly, they are researching their targets to find device-specific credentials. Next is what vulnerabilities are exploited in the IoT traffic. TORCHLIGHT identified 45 vulnerabilities, and 29 of them were zero-day exploitation with 25 CV assigned. And as you can see in the table, 14 of these vulnerabilities are rated as critical severity. And for the estimate price, based on VonDB algorithm, the estimate price of these vulnerabilities are over 300,000 US$ in the exploit market. Even more worrying, we estimate these vulnerabilities affect about 12 million devices exposed on the internet. The most prevalent one is an access control vulnerability that involves privileged access of a Dahua DVR device. We also found a clear trend of attackers targeting legacy, end-of-life products that no longer receive any security updates. To quantify the activity, we create custom three-color rules for vulnerabilities we found. Over 12 months period, we detect more than 90,000 exploitation attempts targeting these specific vulnerabilities. And the chart shows a clear peak in activity. The drawing exploitation peak contributes to past traversal vulnerability, and the lowest exploitation only happens twice in 12 months, highlights the effectiveness of LLM-based IoT traffic analyzer. This is a case study on the infiltration process of a DLinkNAS attacker. First is reconnaissance. The initial request exploits one information distort vulnerability to get device or firmware information, and subsequent requests test for hard-coded credential vulnerability and a command injection vulnerability by injecting a randomized unique string. Once confirmed, the exploitation freeze began. The attacker used these vulnerabilities to implant backdoor or additional tools like BusyBox to gain full control of the device. Here is a real-world example of the simplest backdoor we found. It only has 3 lines in a CGI file, making the device execute the command in the content type HTTP header and respond the execution result. This shows that attackers employ dependency-linked exploitation to infiltrate IoT devices. In conclusion, our work provides the first clear evidence that attackers are leveraging TOR's anonymity to exploit cloudless IoT devices. Our tool, TORCHLIGHT, identified 45 vulnerabilities, including 29 zero-day exploitation and 25 CV assigned. Around 12 million devices are exposed to severe risks like authentication bypass and command injection. Strong interest from cybersecurity community highlights a critical need for proactive IoT defense, and ethical complexity shall be considered in the similar research. And this is the end of my presentation, and thank you.